General Principles. Good morning, everyone. Welcome to Statics. I will be guiding you through this course. Statics is one of the fundamental subjects in engineering because it helps us understand how forces act on structures and mechanical systems that are in equilibrium. The concepts we learn in this chapter will become the foundation for more advanced topics such as structural analysis, machine design, and dynamics. Today, we will begin with the basic principles of mechanics, including fundamental quantities, Newton's laws, units of measurement, and problem-solving procedures.
Objectives. We will begin our study by focusing on the fundamental principles of statics. In this lecture, we will learn the basic quantities used in mechanics, such as length, time, mass, and force. We will also discuss important idealizations, including particles and rigid bodies. Furthermore, we will review Newton's laws of motion and gravitation, understand the SI unit system, learn proper numerical calculation techniques, and introduce a systematic procedure for solving mechanics problems.
Mechanics. Mechanics is the branch of science that studies how bodies behave when subjected to forces. It can be divided into three major branches: rigid body mechanics, deformable body mechanics, and fluid mechanics. In this course, our primary focus is rigid body mechanics. Within rigid body mechanics, statics deals with bodies in equilibrium, while dynamics studies bodies undergoing acceleration. Understanding these distinctions helps us select the appropriate analysis method for engineering problems.
Historical development. The development of mechanics spans thousands of years. Statics emerged first because ancient civilizations needed practical methods for lifting and balancing loads. Archimedes made significant contributions through his study of levers and buoyancy. Later, Galileo investigated falling bodies and motion, laying the foundation for dynamics. Isaac Newton then unified these concepts through his laws of motion and universal gravitation, which remain fundamental to engineering mechanics today.
Fundamental concepts. Before solving mechanics problems, we need to understand four basic quantities: length, time, mass, and force. Length describes size and position. Time measures the sequence of events. Mass represents the amount of matter and inertia. And force is an interaction that can change motion. Engineers often use idealizations to simplify analysis. A particle has mass but negligible dimensions. A rigid body does not deform under loading, and a concentrated force is assumed to act at a single point.
Newton's laws of motion. Newton's laws form the foundation of classical mechanics. The first law states that a body remains at rest or moves with constant velocity unless acted upon by an unbalanced force. The second law relates force, mass, and acceleration through the equation F equals ma. The third law states that every action has an equal and opposite reaction. Newton also proposed the law of universal gravitation, which explains the gravitational attraction between masses and leads to the concept of weight.
Units of measurement. Engineering calculations require a consistent system of units. The International System of Units, or SI, uses meter for length, second for time, and kilogram for mass. Force is a derived unit called the Newton, defined as 1 kilogram meter per second squared. Standard gravity is approximately 9.81 meters per second squared. Consistent use of units is essential to avoid calculation errors and ensure meaningful results. The International System of Units, SI. The SI system includes prefixes that allow us to express very large or very small quantities conveniently. For example, kilo represents 1,000, mega represents 1 million, and micro represents 1 millionth. In engineering practice, prefixes should be converted into powers of 10 during calculations. It is also important to follow SI notation rules when writing units to maintain clarity and consistency. Numerical calculations. Accurate calculations are essential in engineering. One important principle is dimensional homogeneity, meaning every term in an equation must have consistent units. We must also pay attention to significant figures because they indicate the precision of measurements. To minimize errors, intermediate results should be stored with maximum precision, and rounding should only be performed at the final step of the calculation.
General procedure for analysis. A systematic approach helps engineers solve problems efficiently and accurately. First, carefully read and understand the problem statement. Next, organize the given information and create appropriate diagrams. Then, apply relevant principles and equations, solve the mathematical expressions, and present the answer with proper units and significant figures. Finally, always check whether the result is physically reasonable and consistent with engineering expectations.
Important points recap. Let us summarize the key concepts from this lecture. Statics studies bodies in equilibrium, meaning they are either at rest or moving at constant velocity. Particles, rigid bodies, and concentrated forces are useful idealizations. Force and weight are different concepts, with weight depending on gravity. Newton's laws and SI units provide the foundation for mechanics analysis. Finally, always maintain dimensional consistency and use appropriate significant figures in calculations.